In the previous module, we stated a characterization theorem for mixed strategy Nash equilibrium, and we used this mixed strategy characterization theorem to find the mixed strategy Nash equilibrium for certain games. So we have just stated that. In this module we are going to prove it. If you just look at the theorem, so let me just go over the statement of the theorem once more. So it says that a mixed strategy profile sigma I star sigma minus I star is a mixed strategy Nash equilibrium if and only if the following two conditions hold, and these two conditions should simultaneously hold. It says that for all I in n, for all players, the strategy that you have, the utility at the strategies that are in the support of sigma I star should be equal for all the players. So we use this notation delta sigma I star to denote that this is the support of that distribution. And the other condition was that if you pick a strategy which is in the support and a strategy Si prime which is outside the support, then this inequality should hold. The utility inside the support must be at least as much as the utility outside the support. So if you think carefully about it, these things are quite obvious, as we'll see in the proof. But let us prove it formally. This result will be very useful to find an algorithm to find the MSNE. So before we begin the proof, let us also make a few observations, which is quite obvious but very much important and crucial for the proof to go through. So the first observation says that if you want to maximize, so look at the maximization, you are maximizing with respect to a mixed strategy for player I, and looking at the expected utility of that player. Now the observation says that it will be same as the maximization problem with respect to the pure strategies. So why is that true? So just remember what was the definition of UI sigma I sigma minus I. It was just a weighted average over all the pure utilities at the pure strategies. So if you remember this expression, so this utility can actually be written as the sum over all the sigma I Si, and then you look at the UI Si sigma minus I. So this is the utility that agent I gets when agent I picks this pure strategy Si and other players pick the mixed strategy sigma minus I. Of course, this is over all the Si in capital Si. Now this is a probability distribution. So these are all non-negative quantities, and you are taking a weighted sum of weighted average of all these utilities. Now, how can you maximize with respect to that? Maximize with respect to a distribution. So you are given, so you can think of these utilities as individual numbers. So you have n different numbers, and you are asked to take a weighted average of all this to maximize. So what should you do? The most obvious thing is to put all the mass on the maximum value, and that will give you the weighted average to be the maximum. And this observation is just stating that your maximization value that you get by maximizing over any mixed strategy is going to be the maxima of all those individual numbers. So that is one observation that we can make from here. The second observation is the first equality is essentially from the previous observation itself. Just the difference is now we are considering a mixed strategy Nash equilibrium. So consider sigma I star sigma minus I star is a mixed strategy Nash equilibrium. Then of course this should hold because this is coming from the previous observation. Additionally, it is saying that it should be the maximum value when you are choosing this Si from the support of sigma I star. So it must be the case that your maxima should live inside the support, not outside it. And the argument is quite obvious. You know that if we pick so if the maximizer lives outside the support, then we can actually put the whole amount of mass on that utility, on that strategy. So suppose if we have a SI prime where the maximization, so UI of SI prime comma sigma minus I star is the maxima, and that SI prime is not in the support of sigma I star. In that case, you can put all the mass on that SI prime. That will be a new candidate mixed strategy for player I, and that is clearly going to give a larger utility, larger expected utility for that player. But that is actually contradicting the fact that sigma I star comma sigma minus I star is a mixed strategy in Nash equilibrium. You have found a strategy for player I where unilateral deviation is beneficial. So that cannot happen, so therefore this equality must hold. So these are the two things that we will be using for the rest of the proof. So let us begin the proof. So let us first look at the forward direction. That is, you are given this sigma I star sigma minus I star, which is an MSNE. Now what can we write? We know that by definition of MSNE, this is going to be a maximizer for all the strategies. So when the other players are sticking to the sigma minus I star, the utility at sigma I star should be the maximum. This is coming from the best response definition of MSNE if you want. Now we have also seen that this from that observation that we have made, that if you want to maximize with respect to a distribution, it is equivalent to maximize over the pure strategies. So that's done. Now we also know by using the second observation, the last part of the second observation, that this should be the case for when sigma I star sigma minus I star is an MSNE. The maximizer strategy must exist within that support of sigma I star. So notice that it is not ruling out that the maxima cannot lie outside. It is just ensuring that the maximum SI must lie within the support. Of course, there could be another utility which is equal, and that is also a max. But within that support, of course, that maximum value should be achievable. So let's call this equality as 1, the first expression. Now we are going to write the utility, expected utility at the MSNE in a different way. So now we are taking the weighted sum of over all the strategies for player I. So this is by definition of any mixed strategy. Now currently we are writing it for all strategies, but we know that for the strategies which are outside the support of sigma I star, this sigma I star SI for that strategy will be equal to 0. So we can just remove those values and we can write only for the strategies that are in the support. Now this is becoming another expression. Now we have 1 and 2 which are essentially the same. Now there is a point that we need to observe here. 1 and 2 are equal. Just maybe you can just go and take a look at the expressions once more. You see that we are taking a weighted sum over the set delta sigma I star, and that is equal to the maximum of that set. So when can that happen? Maximum is equal to the positive weighted average. This can only happen when all the values are same, right? So you cannot really have so if there were utilities which were dissimilar, then a weighted average, and assuming that all this, so this is always going to be positive, so you have positive weighted average, and that is going to give you, it should have given you smaller than the maximum. So it can never be the equal, it can only become equal when all these UI SI sigma minus I stars values are the same. So this essentially proves the condition 1. So all the utilities, utility SI sigma minus I star are equal when SI is coming from this support of sigma I star, right? This was the condition 1 that we wanted to prove. Let's move on to condition 2. So condition 2 says that the strategies in the support that should give a better utility than the utility outside the support. Now suppose that does not happen. So this is a proof by contradiction. So suppose there exists an SI which is in the support and SI prime which is not in the support, and the inequality is flipped. So what can happen? It's a very similar argument that we gave a few minutes ago. You just so there was some amount of probability mass associated with this SI, right? So the sigma I star of SI was the probability mass that this strategy profile, MSNE strategy profile, was giving on SI. Now I can just shift that weight to SI prime, right? And we know that because this, so for all the other agents, the strategy profile remains the same. So therefore, the utility for that strategy profile is going to get bigger, strictly getting bigger. So by choosing this new mixed strategy, where we are just transferring that probability mass to SI prime, we are strictly increasing the utility of agent I. But this is a contradiction to the MSNE. So this essentially proves that if it has to be MSNE, this the inequality of condition 2 must be satisfied. So that proves the forward direction, that if you are given a MSNE sigma I star sigma minus I star, then condition 1 and condition 2 should get satisfied. So to prove the reverse direction, the if direction, that means you are given these two conditions. Now you will have to prove that that sigma I star sigma minus I star must be a mixed strategy Nash equilibrium. So what is given to us? So from condition 1 we know that Ui Si sigma minus I star is going to be the same for all the SIs which are living in the support of sigma I star. So let us denote that with a notation mi of sigma minus I star. Of course, this is not a function of Si anymore, because it is going to be the constant. Is going to be a constant for all the strategies inside the support. Now, condition 2 is also telling me that this is going to be the maximum over all the strategies, because for all the strategies which are in the support, this is going to be same. For everything that is outside the support, this utility must dominate, or at least be greater than or equal to that those utilities. So therefore, this must be the max. This mi sigma minus I star, the value that we have found in the previous step, must be the maximum over all the strategies inside the support, outside the support. Okay. So this is the interpretation of these two conditions. Now we'll have to show that the sigma I star sigma minus I star is a mixed strategy Nash equilibrium. So let us begin showing that. So let us write down the expression for utility of sigma I star, utility of agent I at sigma I star and sigma minus I star. Quite naturally, we can write it as before, with the reduction in the strategy space, because we only need to consider the support where the probability mass is positive. Okay, so now we know that whenever your strategies are only on the support of sigma I star, all these Ui values are the same, and that is exactly equal to mi sigma minus I star. So you can just write mi sigma minus I star in this place, and because this is not dependent on SI anymore, you can treat this as a constant in this summation. You can take that out, and for the rest of the sum, so if you are just taking the sum over this values, you know that that is going to be 1, because this is a probability distribution and you are summing over all the positive values. For every other sigma I star Si prime which is not in the support, this is going to be 0. So this must be equal to 1. So that gives me the first equality. Now we have also shown that this value is actually equal to the maximum. That is what we have discussed here. So the implication of condition 2. Now this value, we know that whenever you are picking a strategy, whenever you are picking a pure strategy and finding the maximum with respect to that is also going to be the maximum if you consider mixed strategies. So this is coming from that observation that we made before, right? And because this is a max, so we know currently we have UI sigma I star, sigma minus I star. This is the max over all sigma i's when the other players are holding their strategies to sigma minus I star. This can be written as greater than or equal to the utility at any other mixed strategy profile, a mixed strategy of player I. So that is indeed the definition of mixed strategy Nash equilibrium. What we have chosen, player I and this sigma I, these are arbitrary, so therefore it should hold for all sigma i's and for all I. So therefore we have actually shown that this strategy profile, mixed strategy profile, is a mixed strategy Nash equilibrium. So that is the proof of the characterization result in both directions. In the next module, we are going to see that how we can actually develop an algorithmic way to find the MSNE using this result.